Hello and welcome to this video about using Monte Carlo to solve the following puzzle. My name is Ari Berestiano and this is recorded in 2026, so I worked on this Pluto notebook a couple of years ago. So here is the question. You have a frog, this green thing is supposed to be a frog, standing on the 0 point in the real line, facing toward the positive numbers. The frog draws from a uniform distribution a random number, and it jumps. Let's say it drew 0.4, it will jump to 0.4. If it passes the 1 point, it stops. It will not do that in the first jump, so it draws another uniform number independently of the first one and jump that distance. If now it passes the 1, it stops. If not, it keeps drawing a uniform number independently from the previous draws until it passes the 1 point the first time, and then it ends. And the question, and X will stand for the number of jumps it took to that for that frog to eventually or finally jump beyond the 1.0 point. Okay, so what is the expected value of the number of jumps that will require for the frog to pass the 1.0 point? So this notebook, will put a link to the GitHub repository where that notebook is, as an analytical solution. Okay, but intuitively, if you fix a number n, okay, you can draw and you draw n random points from a uniform distribution independently, you will get a point in the 0, 1 n-dimensional cube. Okay, a point. And the probability that after n jumps the frog still doesn't pass the 1 point is the probability, okay, that the sum of the coordinates of that point, the n coordinates or the n numbers that we drew, is less than 1. Okay, the reason why we like the probability less than 1 because it's a cumulative distribution of something. Okay, so basically what it means is that that point is below the simplex of the n-dimensional simplex. Okay, because what's the probability of that happening? Okay, so the total volume of the unit cube is 1, and the volume of all the points below the simplex, okay, the n-dimensional cube, or it's basically n-1 dimensional simplex below it, okay, up to the origin, is 1 over n factorial. So if you sum all the numbers, eventually if you sum all the numbers from 1 over 1 plus 1 over 1 plus 1 over 2 factorial, 1 over 3 factorial, and so on and so forth, that sum, which is the expected value of that x, will give you the 2.71 number, the E. Okay, so suppose we don't have that intuition and we are thinking about using a Monte Carlo experiment to see what's the expected value. So let's use Julia, okay? And here is a single frog that passed the 1 after 3 jumps. The second one was almost at 1, but not quite, so it required the third one. I can press here this button and say jump, and it will draw another here x is equal to 2, and I can do another jump, another try, and so on and so forth. So the idea is to keep doing that a lot of times, and here it's 3, and then sum all those trials over the x's and divide by the number of trials. It's a Monte Carlo experiment. Here is just instead of the GIF, this is a static version, and you will be able to look at the notebook, how this is being implemented. Okay, this is just a graph, but here is the Monte Carlo. Here I did 25,000 draws, and basically what you do is you keep drawing numbers between 0 and 1 uniformly, independently, sum them. Once the sum passes 1, you record the number of draws that it took you to do that, put it, sum it, add it to the sum, keep summing those numbers, and then divide by the number of Monte Carlo experiments. That's as simple as that. Okay. So if we look at how close we get to the E number, which is this dashed red horizontal line at 2.71, etc. at E, it gets very quickly. This is a very big scale, but it's maybe 1,000, maybe something like that, 2,000 draws, and we are pretty much at E. Here is the error, how far we are from the true number, and we are 3-digit, 4-digit close. It doesn't update much, but in the beginning it's 2-digit close, and then it gets 3 and 4 and so on. So that's the Monte Carlo simulation. So these random frogs, on average, will take 2.71 and so on tries until it eventually passes the 0.1 on the real line. Okay, thank you for watching, and I will put in the comments the link to the GitHub where there are such the notebook and other documentation for implementing this. Thank you for watching.